Good morning, everyone. I am Bahadur from TFR Mumbai. Today, I am going to talk about a bit which one is well-established field now, and other is which is starting to come up. In fact, in India, I think it's very recent. So, first part I'll talk about the chiral electrons, and we know various examples of that. And towards the end, I'll also talk about chiral phonons, which are driving many phenomena. Of course, I will start with the people who do the work. So, majorly my group works on first principle theories. Their material specificity is at the center. We combine it with an overlayer of symmetry indicators, which is a topological band theory. And more recently, we are trying to accelerate many of our material specific approaches using AIML. This is my group, but specifically one guy, this Pritesh, is in audience and is also working on this chiral phonon, so more question goes to him at end. We work closely with various experimental and theoretical groups all over the world with this one, and you can visit our website, okay. Sorry with the throat. So, the outline of my talk is this. I have divided into 3 sections. I'll start with topology and chirality, which is a general introduction to the field. Then I will focus on electronic chirality, specifically realizing the topological Weil semi-metal, where we'll show our material prediction and show how the chiral phonon actually drives very emergent transport phenomena. And towards the end, I'll focus about the chiral phonon, and especially one of the exciting recent material is platinum bismuth 2, which is the, I think, only system that shows surface superconductivity in the fermionic states. Okay. So, as we know now, topology, and this audience don't need a broader introduction, but topology is emerged as actually fundamental characterization principle for organizing quantum state beyond the conventional symmetry breaking state, and a particular topological state is characterized by numbers called invariant. And just by calculating the band structure, you can put it in context, and there are a lot of, or in fact, there is a zoo of topological materials. You have topological insulators, crystalline insulator, and you can also have a Weil semi-metal and so on. But specifically, if you look over this region, we have a Dirac semi-metal where you have it's purely a more like a symmetry, symmetry Lego, where you can break symmetry or not. So, you have a Dirac semi-metal if you break time reversal, or inversion symmetry, you split each Dirac points into 2 Weil nodes, which have well-defined chirality, which is plus and minus. If you combine 2 plus charge Weil nodes with some rotation symmetry, you can have higher chiral charge, and in fact, you can up to have 4 and so on. So, basically using this catalog, or you can have many of the quasi-particle which are first time seen in the condensed matter system. Okay. Now, of course, when I look over this one, it's again a highlight for our group's work. We recently started combining all first principle framework to a database. So, this is our in-house workflow, where you start with structure and you finally generate the band structure. This is a website, but will be operating soon. What new on this, our characterization tool is not only we can characterize topological state, but now combine it with the deep learning model, that is self-supervised clustering called contrastive learning. In this database, what you have to just give is you give the target band structure, and it will tells you what all materials are there in the system. Okay. So, of course, this whole the project started with having a curated data set combined with the deep learning model for accelerating the material discoveries. Okay. And this is what the output sometimes look like. For example, if I want one particular system which has band structure similar to this one, not only insulator, because there are also some other insulator depending on where our gaps, but it also characterize the dispersion as well. Okay. Okay. Now, coming to the topic of today's talk is chirality, and we know chirality is actually a fundamental concept for life, and we know from DNAs and all, and also it's a central theme for inertial specific synthesis in chemistry, so biology and so on, and it has widespread applications. And chirality exists in 2 forms basically, or in other sense there are 2 ways to describe chirality. One is static chirality, as in case of our hands, which is static, they are not mirror superimposable on each other, or you can also have a chiral motion like Hall01 motion and so on. But of course, based on just while looking images or their response, we have to look for as a physicist. So in physics, what we define is based on symmetries, okay. So in physics, there is not a unitary equivalent of P transform. So basically, if you, there are two images are not inversion symmetric, and there are two sectors L and R are distinct, and there are no improper symmetries and so on. But what important is these two left and right chiral objects, there is no way to make left to right or right to left without really breaking the objects. So therefore, your chirality emerges as one of the fundamental topological number. That's a, and one example, as we know, is a quantum Hall effect, where when you apply a very strong magnetic field, what happens is you have make an insulator at center of the unit cell, wherever over edges you have a conducting state. And if you say this is motion is only along one direction, so itself is a chiral, and this is encoded in, of course, a very curvature, and you define shear number. And this importance of this one we all know, now it define the quantum standard of resistance, okay. So now, of course, when we see the quantum Hall state or all these states, they require a very high magnetic field in laboratory frame. So one can ask natural question, can we have such fascinating particles even in the materials, okay. And the question is yes. If we now go back and look our Dirac equation, if you start with the massive Dirac, and in a massless case, you have two sectors. So basically, this is a doubly fourfold degenerate point is Dirac. And now if you project your Dirac equation in a chiral basis, you can split into two objects with a positive and negative chiral charge. And these are Weil, no, we call in here is a Weil quasi-particle, and they are actually the low energy excitation in materials, specifically called the Weil semi-metal. And in fact, these two plus and minus are source and sink of Berry curvature, which is a magnetic field in momentum space. And in fact, this is also not only they have a fundamental reach, but they gives the first realization, experimental realization of Weil fermions in, of course, solid state physics, okay. So we started working a long back while I was doing my postdoc. So from there, this journey started from trivial to topological insulator. Now at end we find, of course, if you can stretch the critical point in a system with additional symmetries, you can have a topological semi-metal, and if you have a right set of symmetries, you can realize two kind of semi-metal. One is this band inversion semi-metal, where these points are generic, or you can have a high symmetry points. It all depends on if you have a non-symmetric symmetry. But the take home message is in your Weil node there are two splitting, and these Weil nodes are connected by something called Fermi arc state, which we talk in following slide. And in this particular case, symmetry enforced Weil semi-metal, where the Weil node is at the corner or the high symmetry point of the brilliance zone. There your Fermi arcs actually traverse the full brilliance zone. So it's a very large chiral states. Okay, so this is our first family which I am going to talk is rare earth aluminum germanium. This I proposed in 2016-17, later theory published in 18, but we have experimental verification that comes hands in hand. So this particular family of materials, they have a body center tetragonal lattice, but they have a screw rotations. So in other sense, if you see the local site symmetry, that is orthorhombic, although the whole symmetry of the system is tetragonal. But they don't have any inversion symmetry in the system and but traditional mirror planes. So if you calculate the electronic structure, we can clearly see these valence and conduction bands are dipping to each other. If you switch on the spin orbit coupling, there is various kind of gap opening, but if you explore now this band structure in full brilliance zone, you find in these crossing is forming the nodal line, but with spin orbit they all forms the Weil node. Although it looks a bit crowded and dirty picture, but these are very clear in the sense there are only two planes in the brilliance zone. One is KZ0, other is this plane. And in fact, these Weil nodes are very close to Fermi level, and these are verified experimentally by our collaborators using RPES. Okay, so in this, then we can characterize only these three categories of Weil nodes, and depending on how they are lying from the Fermi level. Okay, Now, one exciting thing is now we are dealing with rare earth, and we know rare earth has all set of magnetism and whatnot states. So, this gives an inherent tunability. For example, if the system is inversion asymmetric itself, now you combine it with magnetism. And if you combine it with magnetism, you can have now inversion breaking. Now, further, these cones are also described based on if they are really Dirac type or tilted dispersion. So, type 1 and type 2. So, this whole family give us a full zoo of all variety of Weil semi-metal, whatever theoretically predicted, like type 1, type 2, eye breaking and all. Now, one question one naturally can ask, of course, there are a lot of Weil nodes, what new physics they can bring up, right? Because that is why we are looking at. So, for that I discussed this particular case, cerium aluminum silicon. It's the same lattice, but it has a very fascinating magnetization. It has a non-collinear ferromagnetic structure. If you see the two cerium sublattices, which is encoded here, so it has a locally, if you look along, its x-axis on another, its other side. And if you calculate now the band structure, it's similar to that, but you have a non-collinear spin structure. This is the first thing in this particular system, and its easy axis is not along 111 or any, but it has to be along 110. This is from the magnetization. Okay, and in fact, this was the first non-collinear ferromagnetic Weil semi-metal at the time. So, what important happen is the sample prepared by one of our collaborator at Boston College, Faisal Tafti, they find a very interesting phenomena. What they see is, if they measure this Hall response or in these samples, depending on where is the Fermi level, the Hall loop shaped, and whenever the Fermi level, for example, in this S4 or S3 or S4 sample, when lies close to the Weil node intersection, it give rise to a very loop shaped Hall effect. At that time, this is a new Hall effect, we named it as a loop shaped Hall effect. And of course, and also this is Fermi level driven, whatever we were proposing theory, later also verified, like the Fermi arcs really playing a role in the system, and this has this is really active over the recent years. Okay, the other important aspects of what these combining a different materials and also the magnetization and associated inherent state, we recently got the paper, but here is now if instead of silicon, if you now mixed the silicon sides with germanium. So, this is there is a change in the Néel temperature in the system because towards the other, and this is a scaling. What more exciting is that depending on what is your concentration you are mixing with, cerium silicon is both Weil semi-metal, germanium is also Weil semi-metal, but depending on the mixing, now if you see about the lower end, this region of it, you will nicely see the magnetoresistance is a circle, whereas in the middle region, it started with smoothly and then there is a singularity in the simple. So, we call it singular angular magnetoresistance, and if you go towards other, this also evolve in the sense. So, this was because the samples throughout we characterize, this took us, like you see this published in 2026, but this has been started from 2018 and so on. So, there was a lot of back forthing and understanding the results. What happened basically in that, if you go from this end to this end, there is the magnetic axis becomes softened, and due to that it has really a non-collinear structure in this system. And there are basically three take home is that depending on where is your Fermi level, your chiral interaction become dominant. This is the Fermi surface and the Weil node distribution of silicon versus germanium. We have just plotted in the other half of the brilliance zone, and also depending on what is the distance between the Fermi level and Weil node, depending on that the singular angular magnetoresistance changes. So, basically by changing the crystal electric field due to going from silicon sample to germanium, and also due to enhanced spin orbit coupling and electronic structure changes, because this become a bigger pocket, and so your interaction, or in the sense the nesting is enhanced, and therefore the chiral interaction between these fermion increases, which gives to the non-collinear, gives the singular angular magnetoresistance in the system. Okay, so far with the electrons, so far I was only talking about the static case where your the chiral or Weil fermion is generated by breaking the inversion symmetry, but itself the structure is achiral. Then there is another way your system itself can be a chiral structure, like you have a absence of any roto-inversion symmetry like a chiral system. So in this particular case, your high symmetry points itself are Weil nodes, and this gives you a large set of Fermi arcs. And we characterize it, there are actually 65 chiral space group and thousands of chiral material. And in fact, the cerium and rhodium, these are some of the verified system. But in this particular, they are very exciting for this proximity induced superconductivity, and that we showed in one of the system recently, which is this B20 multifold Weil fermion semimetal. So in this, it has a chiral structure, and that chiral structure gives you a very large Fermi arc surface state. So these are two high symmetry point gamma and m. They traverse all the way. And what else we calculate is, it's a busy slide, but just very quickly I see. So due to those, it can show it has a superconductivity inherent in it, and our proposal is these all states which is participating in superconductivity are having a well-defined chiral charge. Okay. And due to that, we characterize the different state of superconductivity. So it can, you can see there are various topological superconducting state that exist. But of course, this is a theoretical proposal. We put a coherent picture, and Professor Amit Agarwal is also here. So we did it together for like, again, 5-10 years, if I am not wrong. But at the end of the day, we provide a full coherent first principle pictures to at least deal with topological superconductivity in material aspect. But as we know, this is much more debatable and require a different way of this one. Okay. Okay, so for electrons, so now I quickly jump to the chiral, the phonons. As we know now, no electrons have well-defined spin, orbital charge, and all degree of freedom that interact very nicely with the fields. Okay. However, we also can have phonons in the lattice, and they are very, the particle, you know, they are quasi-particle, but they have zero spin, zero orbital, there is no charge and all. So people were looking, can we find something where you can fine tune? And in fact, one has already proposed a lot of time, people has a topological phonon as well, but we have that aspect as well, but we decided to look, can we have a next degree of freedom? And in that sense, this paper really served a benchmark in 2014 that shows basically you phonon can have chirality and so on, and that they show is in the TMDs. And in experimental verification comes in 2018 using infrared absorption spectroscopy. Okay. So what at nutshell basically is, as we know, all with the lattice vibration, there can be circular motion, and that gives us the phonons, right? And this can have, in other sense, angular momentum associated with it, but is it really a true chirality or not? For that, one has to really calculate this, look at the symmetries. It has a broken inversion symmetry, and if this k dot L is not, or in other sense, if you reflect L to R by some symmetry observations, then you can have actually the true chirality in the system. And what we were doing is basically doing the first principle calculation, combined it with the first principle framework. We showed like the phonon angular momentum can also couple with this momentum to give you the chiral structure in the system. Okay. So this is the focus of our interest is platinum bismuth 2. It has a very fancy physics associated with it. If you look, it has the centrosymmetric structure, and it undergoes a symmetry lowering distortion. So what happened is this central bismuth atom from here is just moved away from the layer. Due to it, it breaks inversion symmetry, and due to broken inversion symmetry, it shows a very nice Weil fermions, very clean arcs, and so on. And in 2025, or towards the end of last year, experiments comes, they shows it has a I wave superconductivity, and that superconductivity is on the Fermi arcs, not in the bulk. Okay, so this is, I think, the only system which has now over the years is really generating a lot of excitement to find a candidate for topological superconductor. What we find is we find a switching pathways from one end to other end. If you see, this is a centrosymmetric structure which is also locally symmetric, and it goes towards the other end, which is inversion breaking P3M structure. And if now we calculate the chirality, or in other sense the angular momentum of phonon, this is the inversion symmetric structure with all same color. So here color means up and down angular momentum. So along the gamma m direction, which is not the mirror in this particular state, we have the chiral phonon. Okay, and now if you just characterize this, for example, I just plotted it on specific direction gamma to m and m. There is a chirality switching from here to here. You can see the two motion of the bismuth atom, or in other sense the over is opposite to each other. So this gives a really chiral phonon. But on the other hand, now not only the motion but itself, one has to characterize the pseudoscalar quantity, this j dot k, be defined. So this is what is showing is a zero plane as you go towards up. This is really enhancing. So the system is really having a 3D chiral object, or in other sense the helical motion in its angular momentum and so on. Okay. With that, now what interestingly, one more interesting object is if you look over these phonons here along this is acoustic and optical transition, and this looks a gap along high symmetry direction. However, if we really explore in full brilliance zone, this shows a very nice Weil nodal line, but these nodal lines is not now a traditional nodal line, but they are actually a switching point between a left chiral to right chiral phonon. And along this there are two set of nodal lines, but not along the high symmetry direction but on the generic point, whereas this nodal crossing occurs as the Weil node. So we are just trying to say these nodal line can be characterized as a switch between the phonons. Okay. Since I am short and also I am done, so this is the summary of my talk. I try to give a bit faster way the chirality both in electron and phonons, and thank you for your attention.
I have a question about, I keep hearing about spin selective transmission of electrons to the chiral DNA molecule. Can you comment on that? Because there are chiral phonons, less of in-orbit coupling, orbital effects. So what's going on? I'm not thinking about it. I'm trying to understand it.
Yeah. So actually, if we consider, in fact, we are already talking about the angular momentum. So spin is the angular momentum. So in this particular case, our the orbital angular momentum is giving all the responses rather than spin. So and that angular momentum is happening due to motion of the orbitals or motion of these atoms. We can discuss it in more, but this is basically not only the spin but the orbital motion of atoms. Yeah. So it's really now, and that's where the chiral phonons comes into picture, and now people are talking about chiral sensors and all based on the chiral phonons and so on. We just started, and this is unpublished, but we hope it will be here.
Yeah, hi, Bahadur. Yeah.
Oh, hi.
So, just clarify that. So this helical motion that you are getting in the Fermi arc in your system, so your Fermi arc becomes helical.
Yeah, so in that sense, okay, I didn't stretch much on that, but if you see the Fermi arc itself is connecting the two chiral objects from left to right, so it has to be direction dependent. In this particular, it's really helicoid because one nodal point is within that the middle of zone, other is there, so they have to connect. So they are connecting like helicoid form. Yeah, so Fermi arcs is a chiral object actually.
Yeah. And second one, in one of the slides you mentioned that your Fermi arc looks like a topological superconductor. So why do you claim that?
Oh no, I didn't claim that. That is experiments. So experiments, they showed this system Fermi arcs become gapped. You see, okay, there is, I didn't put the scale. I think I just picked one of their picture. So in this way, this is actually plotted the gap around this is gapless, and at some point the Fermi arc become gapful. And this they have also measured it is I wave superconductivity with various techniques. Okay, so they claimed it I wave superconductivity, and that is in the Fermi arcs. Okay, that is experiments, not theory. And in fact, there is no way in theory we can say if Fermi arc becomes superconducting or not. We can only say what I have basically telling here. You combine first principle, then Miguel-Ilishevich theory, and you can also do it in chiral phonon setting, and then do the full first principle characterization of the states participating in the superconductivity.
Even in the experiment, if you Fermi arc becomes gapped, it may not be topological. It can be trivial also.
I agree, but yeah, this is a full field that is going on for a debate.
Thank you for the nice talk. In the very beginning, you mentioned about deep learning model for determining materials based upon their topological packet structure. I wanted to know whether it is based on inverse design using graph neural networks or something else.
Okay, so the ultimate goal is of course the inverse design, and we find topological material, doing inverse design for topological material that realize in laboratories we find not that easy. So this is only the clustering of whatever we have 10,000, 20,000 materials, can we cluster them on our way of seeing the band structure. So this is a deep neural network where we are just clustering the band structures. Okay. And of course the ultimate is we have GET I highlighted there, you can combine with your understanding driven design, and we find you can actually find a inverse topological insulator or inverse design topological insulator.
So time for maybe a young guys. You also have one. We will start with the young guy.
Sir, I have a doubt that you have shown the rare earth element is showing the Weyl part, but that can be also shown that heavy fermions, it can be a heavy fermions also, right? So how will you?
Yeah, in this particular case, because the bands which are around the Fermi level are all coming from either silicon, not rare earth. Rare earth's only job is to provide magnetism, nothing more than that.
Okay,
Yeah.
but mostly there might be a case for the, you showed that unconventional superconductivity. So it is related to rare earth elements also. So how will you?
Okay, no, in principle it's true, but whatever system we are talking about Dirac and Weil, their dispersion is quite large. Okay, so linear dispersion, so there is not, yeah, but in principle this is possible because if your state has to be the heavy or the rare earth state near the Fermi level.
Yeah, because in terms of heavy fermions, it has a heavy mass, whereas here it is massless. So that is a.
Yeah, we can talk.
Okay, so you talked about this chiral phonon, right? So in that thing, suppose this motion, whatever you have shown, that in XY plane. So what happened in the Z direction?
So this is exactly because motion is in this one, but your angular momentum is Lz. So that's where it is chiral in the plane, but it is not a straightforward just a circular motion. It's kind of helical. Yeah, it's basically a helical motion. Sorry. Yeah, thanks for saving. Yeah.
All right. Thank you, Bahadur. Thank you very much for